if you want to build intelligent systems, the first step is to look at nature. So the brain is an existing proof of intelligence, and like the birds, where it has an existing proof of intelligence maybe 2 centuries ago, when we tried to build machines which are heavier than air that can fly. So the question arises, should we copy the brain? Maybe like mankind did some time ago, they copied birds to build flying machines. The answer is no, but we should draw inspiration from it. So what is the design principle of artificial intelligence networks? So they're built with many simple units, which together form a complex architecture can be used to solve a task. Then the system learns from examples. So we don't tell the system how to solve a problem, just what we solve this problem. So we show many examples what we want to get. And finally, an important notion is to generalize to unseen events. You don't want the system to memorize the whole world. You want it to be able to react to something it hasn't seen before, but is similar to known stuff. So the basic unit in the brain is a biological neuron. It's a figure on the left, but that's very complicated. It's the basic functioning. You have a couple of inputs called dendrites, which collect stimulation. Once the stimulation exceeds a threshold, the neuron reacts itself and has an output. And this is simulated with what we call a perceptron. It's a very simple unit. What does it do? It computes a weighted sum at the input. If the sum is higher threshold, you have +1 at the output. If not, it's -1. So the weights of this unit are obtained by learning algorithm. So basically, the idea is simple. We present an example at the input. We look at the current output. If it's correct, basically we do nothing. If it's wrong, we correct the error, so it is better next time. So I have to insist, this is not a copy of a human neuron. It's just really vaguely inspired by a supposed functioning of it. So obviously, the brain has not only one neuron. We have plenty of them, a huge number. But actually, the knowledge and learning is not the number of neurons, it's the connections between the neurons. So if a baby is born, we almost have the final number of our neurons, but the connections are changing. So how is learning done in the human brain? So first of all, there's no area in the brain which is like a global supervision, which tells which way to change. This process is local. And as I mentioned already, this is a modification of the synapses, so the weights are changing. How knowledge is represented in the brain? So first of all, it's distributed. You cannot say this weight is the English language, and this is how vision functions and stuff like this. It's overall. And it's hierarchical. So on the right side, you see a scheme how the vision is working. So you have a signal from the eye, and then it goes through several steps until you have the image in the brain. And another topic, it's highly parallel, so all the neurons work together. So how we copy this behavior in our artificial neural networks? So basically, we have a big network of many perceptrons. For this reason, we call it a multi-layer perceptron, which are organized in several layers. Here in an example, you have an input, and then we have what we call hidden layers, and you get an output. And then you have, maybe you've heard about this famous algorithm called backpropagation. You observe an error at the output, and you can infer how to change the interior representation of the knowledge so that you correct that error. And now, what's typical for deep learning? So it's the presence of a large number of layers, and these are organized in a special way. So let's look at a very easy example. You want to recognize images. Let's say you want to distinguish a car from banana, from a beach, on trees, and all kinds of stuff. So the old way, you have an image, and you design, so a human designs what we call a feature extractor. Maybe you want to detect lines, or you want to detect color or continuous regions. And once you have all these features, you train a system to make the decision. Then the next step would maybe to have 1 or 2 levels of features, and then you train your classifier. Now the main idea of deep learning, to see the whole pipeline as one trainable system. The system itself decides which type of features it wants to extract, how to organize them in a hierarchical way, and at the end to classify it. And this is trained end to end, from the very beginning to the end. The system operates directly on the basic representation of the task, in this case the pixels. And for vision, it's very easy to visualize. We have the same architecture here again, and if you see at the left, you have basic features like lines in different orientations. Then you go to higher level, you have parallel lines, maybe circles. And at the end, even higher level, and you can do your classification on it. But all these representations are automatically learned. So there's no human intervention. So to summarize, so deep training or deep neural networks, these are architectures. They learn hierarchical representations. And what's very important also is that the architecture is specific to the domain. If you want to build a system to do speech recognition, or computer vision, they're completely different. They need to be adapted or specific to the system. Then, this is not completely new, but what changed during the last years is that we need two things. First of all, enough data to train the systems, so typically examples, and also machines which are able to train the systems, complex architecture in a reasonable amount of times. So we're speaking about days or weeks, sometimes even up to a month. Here are two examples of recent progress. So on the left, we have object detection over the last 10 years. And you can see from 2006 to 2010, there was some progress. And then you have a type of a plateau. So traditional technology, we didn't improve anymore. And then came deep learning. And it's pretty clear how you can see a steep decrease of the performance once deep learning was introduced. The same holds for speech recognition. There was some progress, then the plateau, and then you got the deep learning, and in this case it's an error. It's an error rate, so the error rate goes down. Here I have an example of typical applications, but before going to the applications, I will try to play a short video which shows you a demonstration. The first one, there's no sound. The system tries to recognize different spots. So the first ones are easy ones. And you see the top value, it's basically a probability, how the reliability the system thinks that it recognized correctly. In most of the cases, it's close to 1, but sometimes there are some doubts. Now we get to a little bit more unusual spots. And my favorite is actually the last one. I'm doing mountain biking, but I didn't know that this exists. Unicycle mountain biking. So basically, this is a complete application. The human speaks, you have speech recognition, then the system needs to understand what is the question. At the same time, the image is analyzed, what is in the image, and the system tries to give an answer. In this case, the answer is just a word, but we could also imagine a full sentence which explains.
Is the baby sitting on his lap?
Yes.
Are they smiling?
Yes.
Is there a baby in the photo?
Yes.
Where is the baby standing?
Bathroom.
What is the baby doing?
Brushing teeth.
You also have probabilities of
What game is being played?
Soccer.
Is someone kicking the ball?
Yes.
What color is the ball?
Yellow.
What game is the dog playing?
Frisbee.
What color is the dog?
Black.
Is the dog wearing a collar?
Yes.
That's a small detail.
What is the cat sniffing?
Banana.
Where is the cat?
On bed.
What color is the cat?
Black and white.
What color are the bananas?
Green.
So here are other examples of successful application of deep learning. So different areas like image classification. You can use it to search in photos. Then all types of video processing. So spot identification you have seen. You can try to detect pedestrians. Then natural language processing. So machine translation is a huge topic. Maybe you have used it already. And all types of multimodal applications where you have maybe image and vision and speech all together. So what is the current status of research in deep neural networks? So I think there are a couple of areas which are very specific where machines outperform humans. Typical examples are what, let's say, computational games like chess, more than 10 years ago, and now 6 years ago. And in image recognition, we already have human performance now that was tested. Then there are areas where more progress is needed. It does work already, but it's not perfect, in particular with language and reasoning. So the example is machine translation. Maybe you have used it already. Sometimes translation is perfect, sometimes it's less perfect. Then more complicated tasks like summarization, or complete systems with question and answering and dialogue. But to finish, we are still far away from building machines with some form of generic intelligence. So in the early years of artificial intelligence, they wanted to build something called a generic problem solver. So this is still not possible. Thank you.